All right, so to start with, I'm certainly grateful for inviting me to this event, and I'm forever grateful to Alexander Yurievich Vertennikov. My journey to probability started with the joint seminar that was run by Vertennikov and Bulinsky when I was a second year undergraduate student at Moscow State, and there are things that I really fundamental things I learned from Alexander Yurievich, like data integration or the Frieden-Wenzel theory that I'm going to mention in this talk very soon. And he has been supportive throughout my career, really. And I visited his home when he was in the US and also in Leeds, and I always appreciate his warmth, kindness, and mathematical professionalism. So this talk is about rare transitions in noisy heteroclinic networks. It really is, it belongs to this area of noisy perturbations of dynamical systems. So what you're seeing here, I hope, so this is a stochastic equation. The drift term is B, and that's going to be fixed. And the diffusion has a coefficient epsilon in front, and epsilon is going to go to zero in this talk. The winner process that drives the equation is a multidimensional winner process. The matrix sigma is assumed to be elliptic. Now, probably everybody knows about the Frieden-Wenzel theory of metastability, where transition times between different potential minima, or more generally between metastable states, they are extremely long. They're exponential in epsilon to the -2, and so that's how long it takes for the system to hop from one potential minimum to another over potential wall. So that's a rare event. That's a large deviation event. In this talk, I'm going to talk about a class of models where also there is a metastability picture, but the transition times are much shorter. So they're only powers of epsilon, and so this is based on my joint work with my now former student Hanbin Chen and the postdoc Zsolt Pajor-Gyulai. It's a long paper, so in 25 minutes or so, I'm gonna really just tell you a little bit of a story and not many technical details. So what are these noisy heteroclinic networks? So we say that a system, well, the OD, or the right-hand side B, the drift field, it generates a noisy heteroclinic network if you have multiple saddles in the phase portrait and they're connected by heteroclinic connections. So heteroclinic connection is an orbit that such that if you run it forward in time at infinity, it approaches the next saddle. If you run the time backwards, then it will approach the previous saddle. And these drift vector fields, they do occur in practice. First, I learned about this family of vector fields when I attended the talk by Valentino Framovich. It was about sequential decision making in neural models, and there are other models like replicator models in biology, some gradient flows. This looks fragile because, I mean, in principle, it's very easy to perturb the system so that the heteroclinic connection sort of misses the next saddle under that perturbation. But if you restrict perturbations to a smaller class, so it's actually pretty robust. So what is the probabilistic picture here? So imagine, I mean, I'm interested in the dynamics when epsilon is small. So I'm starting let's say I'm starting right on one of those heteroclinic connections, and then had there been no noise, you would just have been approaching the saddle, well, this saddle, but because there is noise, you sort of jiggle around this, and near the saddle, because the saddle by definition is it's a critical point, so the vector field there is 0. So in the small neighborhood, it is very small, and so in a small neighborhood, the noise is stronger. And so basically, in the neighborhood of this saddle, you perform a sort of a random walk, but sooner or later, you will get due to some fluctuation, you will get either sufficiently far to the right or to the left, and the vector field is going to take over, and it's going to dominate over the noise, and it will start carrying you towards the next saddle, where the same thing happens. And now you make a decision which way to go, up or down at the next saddle, and so on and so on. So I'm using this concrete two-dimensional example. And the way I'm telling you this, I'm doing this on purpose. I'm trying to induce this image that that in this small epsilon limit, this looks like a random walk on this graph, but it turns out that it's completely wrong. It turns out that this trajectory that I'm plotting here, it's actually quite rare, and this is due to a naturally emerging non-Markovian effect in this system. And so I wrote some papers about this about more than 10 years ago, and I think I talked about that at Sinai's summer seminars in Moscow. And so what I'm going to tell you today, so that's an extension of that work. And okay, let me explain how this works. So if I want to study what happened, how the transitions happen in this network, I'm supposed to study sequential exit problems. I want to take an arbitrary path through the network like this. So these are saddles connected to each other by heteroclinic orbits, and I'm surrounding each of the saddles by a domain, and I'm considering a sequence of exit problems. So from the first domain, you're supposed to exit through this edge into the next one, and from the second one, you keep doing this sequentially. And so, what is the probability to follow this sequence? Somebody's mic is all right. So in the neighborhood of one saddle, this is what's happening. So this is sort of the basic iteration lemma. The goal is to obtain a lemma that I can iterate from one saddle to another over the entire sequence. And so suppose I'm starting near the stable manifold. So there's this point x0 on that manifold, and then there's this transversal vector v, and I'm starting somewhere sort of on this vector v, and but I have this scaling. So the initial position is random, but it scales as epsilon to the alpha, where alpha is something between 0 and 1. And you assume that the scaling limit law holds. So there is this limiting distribution of this random variable xi epsilon. And then this lemma says that there are two probabilities, p plus and p minus, that govern the exit through the right edge or through the left edge. With probability converging to p plus, you will exit in a small neighborhood of q plus, this point on the right, and with probability p minus, you will exit near this point q minus. And there is also a scaling limit. So we started with a scaling limit here. So there's a new exponent alpha prime that governs the scaling near the exit point. And one can actually compute this exponent, and this is so I'm not showing you the concrete calculation. I chose not to because this talk is very short. But it turns out that the main features of this scaling limit for the exit point, it depends on how strong the contraction is, how the contraction and expansion near the saddle point, how they are related. So in this oversimplified example, sort of archetypal, so there's this expansion rate lambda and contraction rate minus mu. Lambda acts on the first coordinate x, minus mu is the contraction coefficient in the vertical direction. It turns out that this coefficient of stability, index of stability rho, plays a huge role here. So that's the ratio between mu and lambda. And it turns out that if the contraction is very strong, namely it's measured by comparing alpha rho. So alpha was the scaling of the initial condition. If alpha rho is greater than 1, which means that rho is sufficiently large, so the contraction is strong, then the exit distribution turns out to be to scale is epsilon to power 1, and it is Gaussian, and it is symmetric. The importance of the symmetry is that at the next saddle point, you're going to exit up or down with probabilities 1/2 and 1/2. And so this sort of corresponds to the case of a random walk on the graph. But if the contraction is not strong enough, then the following picture holds, that you exit fast so there's this expansion in the horizontal direction, and you exit pretty soon, and by that time you haven't had time to contract, and so you already exit, but you haven't contracted yet, sort of. And this means that the exit distribution, the exit law that you see here, in the limit, this random variable eta epsilon, it has this limit eta that is one-sided. It is positive. So with its distribution gives all the mass to the direction up, and it means that due to the strong asymmetry, and because alpha rho is less than 1, so it's stronger than epsilon to the alpha rho is stronger than noise. We will see that at the next saddle, the typically you will exit up and not down. And so this introduces this strong asymmetry, and this actually means that very often at many saddles, you are not really making a meaningful decision. Your decision is predetermined by the history of the process, by where you come from. And so this calculation sort of estimates this, how improbable it is to exit down in the second situation, right? So suppose you have exited from the first saddle, you're exited with scaling epsilon to the alpha rho times eta, and now at the next saddle you want to exit down. So the contribution from this point, from the initial condition, is epsilon to the alpha rho, and then the noise is of order epsilon. And so to have this, to realize the exit down, you have, sort of morally speaking, you have that this must be negative. And of course, this is governed by tails of the Gaussian distribution. So this is an extremely small probability. And this means that, to summarize this picture, so this is the old picture from more than 10 years ago, where to compute the probability of following these saddles, you have this dynamics on these coefficients, on these scalings alpha. So you have these scalings, and the next scaling is computed from the previous one by this formula. And from this formula, it follows that if sum of these alphas is less than 1, and then you insist on making sort of a wrong turn, then the probability of of realizing such a walk along this heteroclinic sequence, that probability converges to 0. And this means that although the graph this heterogeneous network may be quite rich. Only some transitions are going to be realized. And so this is an example of a cellular flow. And I assume that this picture is periodic. And there are just 4 types of saddles. They are numerated by numbers 1, 2, 3, 4. And I assume that the contraction coefficients, well, I assume that the index of stability, rho 1, rho 2, and rho 3, associated to saddles 1, 2, and 3. And they are periodic images. I mean, all these are the same. So these are less than 1. So you don't have strong contraction. But I assume in this example, I assume that in this example that rho 4 is large enough to guarantee that the product of all these is greater than 1. So that means strong contraction. And so under these assumptions, the system travels near the heterogeneous network for a very long time, and departing it, is a large deviation. But what happens at times that are not too large? So say you start near this arrow, and first you travel towards saddle 1. You make a decision which way to go, to right or to left. Say you went left, but the contraction is not strong enough, so you are staying you're staying above this edge, and most likely you will go up at the saddle 2, where the contraction is not strong enough again. And so it means that you will stay on the inner side of the cell upon passing saddle 2 and saddle 3. But once you approach saddle 4, the contraction is strong enough to kill this memory. And upon exiting saddle 4 in the direction of the same arrow that I started with, the contraction kills the memory, and the exit distribution is asymptotically symmetric. Its Gaussian scales is epsilon. And now you have a chance to make a transition to this cell. And that's what happens over a certain time scale, actually logarithmic time scale. So what happens is that you make rotations only within these 2 cells. Once in a while, you will be switching between them. So this is like approximately like a Bernoulli sequence. At each round, you choose which at each new attempt, you choose which of those cells you're going to be following. And that's all that happens at logarithmic time scale. So you only have the circulation within this cellular complex of 2 cells, and you don't see any transitions through the blue arrows. And for the neural dynamics, this observation matches their observation that the neural dynamical systems, they only have quite a few patterns of excitations. Sort of the vocabulary of excitations and in these networks the vocabulary is small, despite the richness of the phase portrait. But of course, this picture doesn't tell you anything about longer time scales. It's an elliptic diffusion that we are considering, and so eventually it's going to visit every point on the plane, or maybe this is a torus. That's how you can treat the periodic picture. So of course, eventually you will see transitions into other cells. And so the question is, how does it happen? Can we understand for a system like this, how the invariant distributions are organized? Clearly, the limit is going to be concentrated at saddle points, because that's where the system spends a lot of time. But how does one compute that? And so that's more recent work. Finally, I'm getting to this new to this new long paper, and so basically the task is to quantify rare transitions. So what is the probability? I mean, I told you that, okay, it's more likely to go up because you stayed on just on this side of the edge. But what is the probability to realize an exit from the cell? And so this slide sort of repeats one of the previous slides. But now let's look closer at this calculation for the exit probability. It clearly shows that if I start too far from the separatrix, from the heteroclinic connection, then if I start at this scale, then this probability is exponentially small. But actually, at any scale that is greater than epsilon, the same calculation shows that, I mean, if it's epsilon to any power smaller than 1, the same calculation shows that it's an extremely small event. So it turns out that this is not how these transitions are realized. I mean, if you want to, it turns out that if you want to exit at the next saddle, it's not that you first realize a critical, you realize a typical exit, and then you realize a rare event. It turns out that you have to prepare the exit at the next saddle by certain behavior near the first one. Namely, although the typical values scale like this, it turns out that the exit will be realized only if you realize this unlikely event that this random variable eta epsilon is of this order of magnitude. Because if it is, then the contribution from this term is of order epsilon, and then this exit is possible to do. It has a positive non-vanishing chance of being realized. And the result of this is that we need local limit theorems that would compute these limits. So what is the probability that this scaling, this random variable eta epsilon, we know it converges in distribution, but we need to quantify these probabilities, and that turns out to be extremely hard. It took us many years to compute this, and so this is a very high level form of our result. It turns out that these probabilities are polynomial, or powers of epsilon. There are three situations. So the first one is the old situation. So the realizing such a chain of events may be typical, but if it's not typical, then it's either a power decay of epsilon or it's the large deviation. And proving this theorem it requires quantifying various transitions between various scales. So what happens when you pass from one saddle to another? How does the scaling change? What are even if you look at unlikely transitions? So how unlikely could they be? And so this is the description of it's a high level description of these results. So if you start at scale alpha less than 1, then no matter what, you just exit at scale epsilon to this alpha rho minimum with 1 with high probability. But if alpha is equal to 1, so if the initial scaling is just epsilon to power 1, then the typical behavior is exiting still at the same time scale prescribed by this formula, but there is a bunch of situations where you have that local limit theorem that I have mentioned on the previous slide, and this is what this limit theorem is. So it turns out that probability of exiting abnormally close to the separatrix is it has probability that decays as epsilon goes to 0. It decays as epsilon to some power, and this G is a Gaussian density. Nu is some unbounded measure, not a finite measure. And to prove this result, you need to we used Malevin calculus, and there is a certain iteration scheme that I'm not going to talk about. One interesting fact is that because the exit time is growing, usually Malevin calculus is used for controlling densities of distributions at finite times. So we have to use some tricks to extend this to longer times. But essentially the result is that there is a family of these polynomial probabilities of rare transitions. So these rare transitions are polynomially small. And if the probability to realize such event is epsilon to the theta for some theta, then the associated time scale, how long will it take to realize this exit? It will take epsilon to the minus theta attempts. And each attempt takes logarithmic time scale, because that's how much time you spend in the neighborhood of one saddle. The result is that you have, for various transitions, you come up with, for each transition, you come up with its own theta, and you can order these thetas, and these thetas then determine a sequence of time scales relevant for this problem. And so if the time that you are looking at, it is between those times, then you will see many transitions with for some thetas, you will see lots of these transitions, but transitions associated with longer time scales will not have happened. And this leads to a hierarchical structure of clusters and clusters of accessibility and transition times that is similar to the classical metastability picture. And so let me show on my last slide. I'm back to this example. There's nothing special about this example. It's just something that I'm using to explain these ideas. So what is? I mean, we know that if the time is not too long, we just oscillate sort of within pairs of these cells. But if we wait longer, it turns out that the first edge that becomes sort of transparent, that's going to be the edge from 1 to 2. And that's the associated time scale is this, where ρ1 is the index of stability at saddle 1. And so what you're going to see is that mostly your system is going to rotate within these pair of cells, switching between them. But then at some point, it will go through this edge from 1 to 2 into the adjacent pair of cells. And when it does, it will start oscillating there between switching between these two cells. And then at some point, it will switch back to this one, because that's another edge from 1 to 2, or from 1 to 2. But all other edges are still not transparent at this time scale, and you will not see those transitions. But if you wait longer, then the edge from 2 to 3, the transition through that edge becomes available. And at the longer time scale, we will also switch between these 2x2 squares. So that'll take longer, and now the cluster of accessibility is an entire horizontal strip composed of these squares. And now you can even prove a central limit theorem, because this is sort of like a random walk on these squares approximately at the relevant time scale. But if you wait even longer, then finally the edge between 3 and 4, it will become transparent. Transparent means that now I will be able to see transitions through that edge, and at that point the entire plane becomes accessible. And now we can now prove a central limit theorem in the vertical direction with a different time scale, with a different normalization. So the result is this metastability picture with clusters, with hierarchies of merging clusters and associated time scales that are much shorter than the classical Friedland-Wenzel time scales. And I mean, this picture holds for a much broader, not just for this example, but for all kinds of examples. And one can treat these results now as homogenization results, and you can homogenize the associated PDEs and show that in the limit you will have something like basically the heat equation that corresponds to the Brownian motion in horizontal or vertical direction with different scales. All right, let me stop here. Thanks.